Welcome to Study Loop.
So here we have the x position in terms of time and the y position in terms of time. Alpha and beta are defined, alpha being 2 meters per second and beta being 1.2 meters per second. This would be graphed from essentially 0 seconds to t is less than or equal to 2.0 seconds. So essentially, this would be what this graph is representing. And this would be for part A. Now, for part B, we know that here the x velocity is going to be simply equal to the derivative of the x position with respect to time, and this is simply alpha, and this would equal, of course, again, 2.4 meters per second. So the x velocity is constant. The velocity in the y direction would be the derivative of the y position with respect to time. This is -2 times beta times t. And we can then solve for the acceleration in the x position. This would be the derivative of the velocity in the x direction with respect to t. And this is equaling 0 because the derivative of a constant is always 0. And then for the derivative of, for the derivative of the acceleration in the y direction, this would be the derivative of the velocity in the y direction with respect to t. And this is simply equaling -2 times beta. And this is also a constant. So we have that the velocity vector would be equaling alpha I hat minus 2 times beta t multiplied by j hat. And for the acceleration vector, we simply have equaling -2 times beta j hat. And so these would be your two answers for part B. For part C, now we want to essentially we're trying to evaluate this at t equals 2 seconds. So this would be our velocity vector at t equals 2 seconds. This would be where our velocity in the y direction would be equal to -2 times 1.2 meters per second squared multiplied by 2.0 seconds, and this is equaling -4.8 meters per second. And we know our velocity in the x direction to be a constant 2.4 meters per second. So that would be represented here. And then for the acceleration, we have at t equals 2 seconds. This would all be in the x position. This would all be in the y direction, and this would be -2.4 meters per second squared j hat. And then the acceleration in the x position, or we can say the acceleration would be equal to 0 meters per second squared I hat. So that would be represented here. And we can find the magnitude. The magnitude would be simple to find in the sense that for acceleration, the magnitude of the acceleration vector would simply be equal to 2.4 meters per second squared. The direction, of course, would be straight downwards. And then for the velocity, this would be equal to the square root of 2.4 squared plus -4.8 squared, extend the square root. And the magnitude of the velocity vector would be 5.4 meters per second. And if we wanted to find alpha, essentially this angle here, alpha would be equaling to arctan of the y position, -4.8 minus 2.4. And this is equaling essentially -63.4 degrees. And if we were to then add 360 degrees to this, alpha would equal 297 degrees, and this would be measured from the positive x-axis. So this angle here going around would be 297 degrees for the velocity function. Now, if we wanted to write them in both the x and if we wanted to put them on the same graph, this would be for part D. Apologies. This would be for part D. And we can evaluate. So the acceleration vector has a, we can say acceleration parallel in the same, this would be in the same direction as V. We can also say that if this is the case, V is increasing, this means that bird is speeding up. We can then say that here, the acceleration also has a perpendicular component. This would be perpendicular to V. So we can say that the direction of V is changing. So we can say that the bird is speeding up, and we can say that the bird is turning towards the negative y direction. So this would be our answer for part D. That is the end of the solution. Thank you for watching.